I'll introduce myself first. So I'm Tom, and I'm a lecturer in the School of Mathematical Sciences. In a past life, I did a lot of research in things like polymer physics and computer simulations of particles moving around and crystallizing and doing all sorts of interesting things. So I was very much into my applied maths. These days, I do some research in maths education. So I'm very interested in how to teach maths effectively and how to help students make the transition into university education from school or college. And actually, that's what brought me to want to do this lecture today. So one of the things that I've found over the years as being a really important cornerstone of mathematics is the ability to solve problems, and we're going to explore a bit of that today. So let's make a start. So I'll begin with a quote from a Hungarian mathematician called Paul Halmos, and this is part of a much longer quote where he says, here's the ingredients for mathematics, and he talks about theorems and definitions and proofs and the sort of things that you see in a typical maths degree. But then he kind of ends by saying the bit that I've quoted here, which is actually a mathematician's main reason for existence is to solve problems. So what mathematics actually consists of is problems and solutions. Now, the tools that you use to solve those are the things that you learn at school, and then you learn some more of those things at university. But pretty much, this is my claim anyway for today, I think it all just comes down to answering questions, so solving problems. So let's see if you believe me by the end of today. Okay, so first of all, let's talk about what questions are. So questions are tasks. These are things that arise when you're doing mathematics, and sometimes the answers are obvious, sometimes they're less obvious, and that's where we get to our next distinction. So at least for the purposes of today, I'm going to categorize questions into two types. Okay. Now, the first is a mathematical exercise. So this is a question where you pretty much know what to do. You see it. It's the sort of thing you might see early on in an exam paper where you think, right, okay, I know how to solve that. I'm just going to grab this particular formula or this particular method from my memory or a formula sheet and apply it, and then we get a correct solution. Now, a problem is where actually you have to stop. You can't just go straight into, okay, right, apply that technique and we're done. And what's interesting about when you make these categorizations are, well, actually, whether a question is an exercise or a problem will depend on who's answering it. So one mathematician's exercise is another mathematician's problem. And if you've solved that problem once, perhaps that then becomes an exercise. You remember, oh, okay, I know how to do that for the future. Or perhaps you get to the end of the problem and you say, actually, it's never going to be an exercise. That is a really tricky problem. So let's look at a couple of examples, and this is your first opportunity to have a go at answering one of these yourself. So here's a question. So this is calculating an integral, and I don't actually need you to solve the integral. What I'd like you to do is answer this question. So to you, is this an exercise or a problem? So if you go to that link, or if you click on the direct link in the Q&A, you'll be able to access that and you can submit your vote. So I'll give you a minute or so just to access that question and to submit your answer. Okay, I can see at least 3 of you have been able to submit an answer, so that means the link must be working for at least 3 of you. Now, what I'm going to do, I'm aware that there is a slight lag on the recording. I'm going to start a 1-minute countdown, now, which you're going to hear in about 20 seconds, but the countdown will appear for you anyway, but that'll be more than enough time for you to submit an answer. Okay, right. That's exactly what I was hoping for. So about, well, okay, only 8 people have answered, so slightly more than half have said this is an exercise, and the rest of you said this is a problem. And that's exactly the sort of result that I'd expect, because if you've only just learnt about integration, maybe you haven't even learnt how to integrate sines and cosines yet, then this is a problem, because it's not something you're particularly familiar with. If integration is something you're familiar with, then you might see it as a slightly tricky exercise, because you've got an inverse chain rule to do. You might have to evaluate some trig functions at pi and minus pi. Or if you're even more familiar with these type of questions, then you might just look at it and say, well, sine 2x is an odd function, and if I look at the region of integration, I go from minus pi to pi. Well, I've got just as much area above the curve as beneath the curve, if that's how you like to think of integration, and so they cancel out, and straight away I can just write down that the answer is 0. So you don't even have to do any integration. You can just think of it as a geometric problem. In which case it's an even more trivial exercise, but that's actually because of the experience you have beforehand. So this is a really nice example of a problem that becomes an exercise after enough experience. Okay, so here's another one. So there's quite a lot of words in this one, which some mathematicians aren't particular fans of, but I'm afraid the more advanced maths you do, the more words you see. So you've got this description of a problem, but it's a geometric problem. So the first thing, if you're not provided with one, the first thing I would do anyway is to draw a diagram of what's going on. So this time you've got K, which is a point on a circle, which is sitting inside and touching a stationary circle of twice its diameter. So it's important that the outer, the bigger circle is stationary. What we're then going to do is we're going to rotate the smaller circle around that interior of the bigger circle, and there's no slipping, so it's going to move perfectly. Think of if you've ever had a spirograph, then that might bring back some nice memories of that for you. And what you need to do is describe the path of K as the smaller circle rotates around the larger one. I'm going to ask you the same problem. You don't have to answer the actual question. I'd like you to tell me whether you think this is an exercise or a problem. Okay, I'll reset the, give me just 1 second. I should have done that a bit quicker. I'll just do the survey for you and you can start answering. And what I'll do, I'll put a 2-minute timer on this time, which will more than account for the lag. There we go. Okay, so this time it swung the other way. So I seem to have caught out a few more people with this one. So I think problems like this just inherently look a bit more difficult because of the type of response you have to give. So the first one feels a lot more routine. It's a calculation. There's going to be a numerical answer, and so a lot of people are more likely to say that's an exercise. Once I know the technique, I can get an answer. Whereas this one, I've simply asked you to describe something. So it's perhaps a little less clear exactly what you want. Do you need to sketch the solution? Do you need to describe it in words? Actually, it's quite tricky because you might have to, you might want to make a physical version of this thing and see what happens, or you might want to, sort of draw some little bits of diagrams, maybe even use some algebra to describe the curve. So I can see why more people would describe this as a problem rather than an exercise. It's a bit more ambiguous what's required. But just going through this process of before you even think about actually answering the problem, just sort of thinking, well, okay, what level of difficulty is this for me? What sort of questions do I need to ask? This is a kind of a good first step in problem solving. So, right, let's talk about that a bit more then. So the first part of solving a problem, I would say, is translating it into mathematical language. So that might be having to write down some equations. We drew a diagram for that last one. So if there haven't been one provided, we ought to draw one if there is an obvious diagram you can draw. Because in doing so, then you can actually get a really good concrete understanding of the problem. So what is it exactly that you're trying to solve in the first place? If you don't know that, then how on earth can you come up with a good quality solution? And then once you know what the problem is, you can go into your memory bank, so whether that's in your head or in your notes or online or wherever, of finding appropriate mathematical techniques to attack it. But you can't do that until you actually understand what the problem is. And before you actually start applying those techniques, what you should also think about is, well, what would a solution look like? What sort of things might I have to provide? So is it just a numerical answer, like in that first example? And if so, is it a single number? Is it a range of values? Is it multiple? Are there different solutions depending on the context? So if you're solving a cubic equation, for example, are there going to be? Do you expect to have 3 roots, and do you expect that all 3 are going to apply to your situation? So I don't know. For example, let's say you're solving for something in time, and one of the roots is negative. In your context, does that count? That sort of thing. Are you expecting to not actually get an answer as such at all? Are you actually expecting to find a governing equation? Is your problem to model something, and actually maybe the model itself is the solution to this particular part of the problem rather than actually solving something? Could it be that you need to prove or disprove something, or show that something exists or doesn't exist? So might it actually be some sort of mathematical argument or a proof? Maybe you want to include a diagram or a graph or some sort of written conclusion, and of course all combinations of these things. Sometimes you actually need both. So it's often quite bad practice, I would say, to just supply a numerical answer. So in that integral question earlier on, if you just wrote down 0, then okay, points, that's correct. But actually, you ought to justify that too. As a good mathematician, you ought to also be justifying your answers. So that might be in the form of some sort of mathematical derivation using algebra. You might want to include a graph if your argument is along the lines of positive and negative areas cancel or something like that. You ought to actually show that. So that's essentially what I just said. So typically, when you're solving maths problems, even when you're doing exercises, to be honest, just writing down the answer isn't enough. You need to actually justify what you've done. Partly to be kind to your future self. So when you're reading back through your notes, you'll remember, when you're really in the zone doing a question, you won't be in the zone forever. You'll come back to it at some point and think, how on earth did I manage to do that? Actually, writing some notes for yourself is very useful, but actually even more than that, you're probably going to be presenting your solution to somebody else, whether that's in the form of an exam paper or some coursework, or even just to share with a friend if you're working together on something. So you ought to get good at actually curating or making sense of the mathematics you're doing. And that is all part of the problem solving process. It's understanding exactly what you're doing at all the steps. So to go back to the questions, so translating something into mathematical language, what I'd like you to do is take this statement: there are 6 times as many students as professors at the University of Nottingham. I'd like you to write that down as an equation. Okay, and I'll just set that up on the link for you. That's irritating. Sorry. I try to make life easier for myself, and for some reason I have to reset everything. Okay, right. That should be ready for you now. Okay, so since not many of you answered, I can actually see what's going on here. So right then, so 3 of you have said that S equals 6p. That's good. 6p equals S, that's the same thing. 6p equals S, 6s equals p. Okay, so that's really interesting results. So obviously, so 6p equals S is correct. 6 times number of professors equals students. But anybody who put 6s equals p or p equals 6s, I completely understand why you would do that. So this is a really famous, well, that's not really famous. It's famous to me because I've done it a few times. Kind of thing that happens. It's more of a social experiment than a maths problem, really. But where, because this statement was expressed as 6 times as many students as professors, so the 6 comes before the student rather than the professors, it's kind of, I don't know, something goes wrong in your brain and you just write down 6s equals p, which of course means there are 6 times as many students as there are, sorry, there are 6 times, see, I just did it there. There are 6 times as many professors as there are students, which, you know, and when you say it in that way round, you realize that's nonsense. But this happens all the time. When you get given a big block of text and you've got to somehow translate that into mathematics, you've got to draw equations out of it, you might have to you know, write a table of data or something to summarize what's going on. It's so easy to get things the wrong way round or put things in the wrong context, which then of course means you solve a different problem. You solve the problem you wrote down, which is different to the problem that you were presented with when you did the translation. So I'm glad that at least 2 of you fell into that trap there, where it can be so easily done, and you've got to be really, really careful about being precise and reading every single word of whatever problem you're given carefully, because of course if you write it down wrong at the very beginning, then you might do some very, very sophisticated and correct mathematics, but on incorrect information to start with. So but most of you got it right, so very well done. Okay, so something else that should be said about problems is, so sometimes that's not the issue. So sometimes problems are very easy to state and to understand. So here's an example. So you may have heard of this, Goldbachs conjecture. So it's got a very simple statement. So every even integer greater than 2 can be expressed as the sum of 2 primes. So it's sort of, this is a conjecture. So it sounds like it should be true according to how it's been expressed there. But well, the truth is we have no idea whether it's true or not. And in fact, this has been baffling mankind, mathematicians for over 250 years. So either to find a counterexample or to come up with a convincing proof that this must be true. So what has been done, you can use a computer to generate lots and lots and lots of primes and lots and lots and lots of even numbers, and just check that you can find 2 primes which add up to that even number. I think it's been done something up to something crazy like 4 times 10 to the 18, or no, 4 times 2 to the 18 or something like that, some massive number. But that's not a proof, right? That's just a mechanical, we've found lots and lots of examples of it working. That's different to saying it will always work. So whilst some problems are easy to kind of state and to, so right, this is the thing we've got to either prove or disprove, actually going about doing it can sometimes be surprisingly difficult. So, you know, with this sort of thing, you know, where do you even begin? So, you know, one way to begin might be, well, if we think it's false, we'll have to try and find a counterexample. People have been doing that for a very long time, haven't found one yet. So then you might start to think, okay, maybe there isn't one, maybe that means it is true. Right, so now where do we start? Where do we, what sort of mathematics do we need to use to attack this? And again, that might be surprising. So we might need to discover some other bit of new mathematics in order to come back to this old bit of mathematics to solve it. And that's very common in, you know, so when Andrew Wiles proved Fermat's last theorem, he managed to do that because of lots and lots of other apparently unrelated at the time mathematics came along, which he managed to use. So things like elliptic curves and things like that in order to attack that problem, which had been long standing. So problem solving is very rich. You know, sometimes it's all in the statement of the problem, sometimes it's actually in the creative ways that we use to solve that. So it's very difficult to come up with a robust process, and I can't really be very specific here, because actually the actual process that you use to solve a problem will be entirely depending on the context, and actually to some extent what kind of mathematician you are as well. You might naturally approach things in a slightly different way, and that's fine. But George Polyer suggests the following process, which I think I agree with. I think this is kind of a good general process to go through. So the first thing is everything we've been talking about so far. First of all, you must understand the problem. So have you written down some equations which summarize it? Have you drawn some diagrams? Do you actually understand what it is you're trying to solve and what your solution might look like? You then have to make a plan. This is where you start to draw on mathematical techniques that will be useful. Having gained a good understanding, do it. So you carry out your plan, and then you reflect. So you look back, and you might have to go again. So part of this looking back is, well, I've got a solution. How can I verify whether the solution is right or not? And actually, if you find some problems, you might have to go back, even all the way back to step 1. You might think, well, actually, maybe I didn't understand the problem well enough. Maybe I have to do that again, or maybe go back to step 2, make a different plan. So Polyer proposes this iterative process where it only terminates once your reviewed plan is confirmed to work, and that can often be a very non-trivial process as well. So the actual plans you make, as I've already alluded to, will depend on all sorts of things. It'll depend on the problem, it'll depend on what sort of maths that you naturally lean towards, and essentially what kind of mathematician you are. So I've just suggested some of the ideas that I might have. So you might develop a mathematical model, so a mathematical or a statistical model to describe what you're doing. This is very common, especially in applied mathematics or in probability and statistics. And we have whole lecture courses in mathematical modelling. That's a very involved area once you really get into it, and come to the University of Nottingham if you want to see more about that. Then you might want to make use of some existing mathematical theorems. So there might be some really key results that you might combine in interesting ways to answer the problem, or you might have to devise some of your own theorems. And of course, if you do that, you'll have to prove them as well. So then suddenly your solution becomes more and more involved. You might do something algorithmically. So you might write a computer program. So some examples of languages that we use at Nottingham are Python, R, C++. You may have some experience of doing these already. So you might design a model, first of all, and then you run a simulation using something like Python. You might go and collect some data. So again, you might need to do an experiment, or you might need to go and survey some people, depending on the context of the problem. And of course, you have to analyze that somehow. And almost always it will be some combination of the above. So there'll be all sorts of different lines of attack that you'll need to go down to solve your problem. So for the rest of the talk, we're going to get through some problems. Now I'm looking at the time. We're going to do at least 2, possibly 3 if we have time. But I quite like this problem. So this one's a very old problem, goes back about 1500 years or so. So here it is. So we've got a dog which starts in pursuit of a hare at a distance of 30 of its own leaps from the hare. If the dog covers as much ground as in 2 leaps as the hare does in 3, how many of the dog's leaps will the hare be caught? Now, you can answer this. I just need a number, and our unit of distance here is 1 dog leap. And what I'd like you to think about when you're making your constructing your answer is, what assumptions, if any, have you made? Okay, I'll put 3 minutes on the timer this time, because you might have to sit and think about this one for a little while. Okay, so we've got a whole bunch of answers here. So okay, let's see. So we've got everything from 22 up to 180. So there's lots of different ways. What I like about this problem is there's all sorts of ways that you can approach it, and it's sort of, again, it's going back to what I was just saying about depending on what kind of mathematician you are, you'll have a different plan. So I can reveal the answer is 90. So well done to I'm not quite sure. Okay, 30%. Okay, so that's probably two of you. Yeah. So so the idea here is that, I mean, the way I first thought about this, I kind of thought of the journey of the dog in 3 steps, and then how far behind the hare is it? Okay, so I guess 3 steps if you count from 0, so 4 technically. So at the 0th step, at the very beginning, you've got the dog at the origin, if you like, and the hare 30 leaps ahead. And then some assumptions that I'm going to make. So I'm going to assume that the dog and the hare leap at the same rate. So I can kind of have time steps of leaps, and it just so happens that a dog's leap is a bit longer than a hare's, so that it does 2 leaps and the hare's done, well, 2/3 of that. Or if the hare does 3, the dog's only done 2, and so on. So if you think, okay, so first of all, the dog gets to where the hare started. So the dog's done 30 leaps. And then in that same time, the hare has also done 30 leaps, but has only got 2/3 as far. So the hare is now 20 of the dog's leaps away from the dog. So you see the dog's caught up slightly with the hare, but by 10. So if you repeat that twice more, they'll intersect. So when the dog's gone 60, the hare is now 10 ahead. And when the dog's done 90, the hare's nowhere, it's not ahead anymore, they've intersected. Another way of doing this, you could actually use a graph. So you could do something like this, where you say, right, on this axis, I'm going to have n for number of leaps of either a hare or a dog. So that's like your time axis, if you like, number of leaps done by either. And I'm going to have this axis as d. So this is distance in dog leaps. And the dog is just going to go up here with a line of gradient 1. Oh, okay. So that's meant to be going through the origin. I've drawn it a little bit too high up. So this one here is the dog. So it starts at 0 and then goes, for every leap it's done 1 dog leap, obviously. Now the hare is going to start up here somewhere, up at 30 dog leaps ahead, but we'll have a smaller gradient, right? Because in fact the gradient will be 2/3 if the gradient of the dog is 1. That's what the question tells us. So then what happens is, eventually, oh dear, I've drawn that in a slightly awkward place, but never mind. That's the hare for that one. So what you then need to do is work out, well, how many, let's call it n star, how many leaps have happened. And in my version of the problem where they have the same leap rate, well, okay, in terms of distance, we know that's going to be equal to n star, because our unit of distance happens to be the same as units of time in some sense, because it's either dog leaps or number of dog leaps, same thing. And so obviously n star, you could also work out the d star, but because it's going through this line of gradient 1, that's the same anyway. There are much more complicated versions of this question. So I've seen over the centuries where it's been set, you could do a version of this question where you have some information like I've given you about the difference between the distance a hare leaps in 1 leap and the distance a dog leaps in 1 leap, but then also some more information about the different leap rates. And then of course you would have a much more complicated answer. So you know, if not only is the hare leaping a shorter distance, it might be doing more leaps, but the dog's leaps are large enough that even though it's doing fewer leaps per second, it can still catch up, and so on. So do have a look around online. You'll find all sorts of versions of this problem. It's really interesting. But I guess a couple of key messages from this one is there are lots of different approaches that you can take, but also you have to be really careful about what assumptions you're making. You know, so I'm also assuming that not only do they have the same leap rate, but they leap at the same time. So me and Joel were talking about this one earlier, and he said, well, what if they take it in turns to leap? Then actually you could have a +1 or a -1 depending on who leaps first. So you could have about 89 or 91. So there's all sorts of versions of this that you can look at. Okay, so looking at the time, I'm actually not. It's a shame because I was really looking forward to doing this problem, but I don't want to go over time. So this is my dog Lara. As you can see, I quite like doing questions about dogs. And I did a version of a fairly classic problem where you have a dog running between two owners. I think the original version is a bee going between two model trains, but you get the idea. And you have to work out how far the dog travels before the owners meet. But we'll save that problem for another day. Come to the University of Nottingham and I'll start you off with that problem. Okay, so I just want to leave you with another problem that I really like for a number of reasons. So I'll just sort of let you take it in for a moment. So what we've got here is an infinite lattice. So it's a square lattice, and what that means is that each point is at a particular integer in either the horizontal or vertical direction. So you can put your origin wherever you like. If you go one step to the right, you've moved across by one integer. If you go one step up, excuse me, you've moved up one integer. So you can sort of come up with a coordinate system if you like around that. So I'm then going to define a lattice triangle as a triangle whose coordinates are all on vertex points. They're all on vertex points. What am I talking about? They're all on lattice points. So that all the vertices of the triangle are on lattice points. And the question is, what is the size of the smallest equilateral lattice triangle? So the rule is all three of the corners, the vertices of the triangle, have to be on lattice points, and all three sides of that triangle will have to be equal in terms of this metric that we've defined using these integer lattices. And of course, it means that all the interior angles must be 60 degrees as well. And it turns out that no matter how hard you try, you will never be able to draw an equilateral lattice triangle. Now, you may not believe me. You might think, well, you know, if I just get it at just the right angle, or if I make it big enough, or whatever, have a go. Just try drawing one. But the bigger kind of solution to this problem is, well, now that we've claimed that there are no equilateral lattice triangles, we actually have to prove that. Now, this might be something that you've not actually tried to do before, to prove that something doesn't exist. Often we're talking about finding solutions and finding or showing that something is definitely true. And we can't really do a counter example here because we can't, because that's the point, right? We're trying to show that there isn't something. And so I'm going to leave that with you as something to think about. How might you go about proving that you can't get any equilateral lattice triangles? And what's nice is there are loads of proofs out there. I'll have a go at doing one or two yourself first, and then maybe have a look online to see what other people have done. But there are lots and lots of different approaches to this that you can take, depending on what kind of maths you like. So just to summarize, my claim, I hope you agree with me after all that problem solving is central to all mathematical pursuits, whether you particularly like statistics or applied maths or pure maths, particularly if you like pure maths, I would say. It's really central, and that's probably one of the main things that you'll get out of a maths degree. That's really what makes you employable as a professional, this ability to solve problems using this kind of process we've talked about today. We talked about exercises and problems and how that will evolve in time as you develop your mathematical skills. It's really important to gain good understanding of problems and follow Polly's iterative process to attack a problem, review what you've done, and then confirm that you've got the right answer. And no matter how many problems you've solved in the past, they can still surprise you. And often the solution is that there are no solutions. And I'll leave it at that. Thank you.